end-of-the-world problem at all. It's an exercise made up by math teachers to get you to memorize your identities.
Okay.
In other words, here's an example of one. What they're saying is that is the same as that. And you have to prove it.
Oh, okay.
Now, tell me if you've done this already. I think...
No.
No, yeah, this is coming up. And practice is about the only thing you can do on these. You can kind of get a feel for what you have to do. You have to... Let me think for a second. If we take the left side and we turn it into sines and cosines, they kind of give you a set of rules for what you can do when you're verifying trig identities. And the ones,
okay,
they're not algebra equations. They are, but you're not allowed to do some of the things that you can do with algebra equations. In other words, you can't divide both sides by tan of x, okay? What you do is you select the more complicated side and you try to turn it into the right side. And you're allowed to manipulate both sides, but you're not allowed to move stuff from one side of the equation to the other. That's the big restriction. So if you recall your quotient identity, what's tangent equal to?
Tangent is equal to cotangent?
Sine over cosine.
Oh, okay, yeah.
One of the, like I said, they give you 4 or 5 techniques for doing these. And the very last one is, if all else fails, turn everything into sines and cosines and see if that works.
Okay.
Okay, well, cotangent's what? What is its quotient identity?
Cosine over sine.
Now let's work with that. And let's find a common denominator, which is what?
Cosine plus sine.
Cosine times sine.
Times sine.
Okay. And then up here, that must turn into sine squared of x. Right.
Mm-hmm.
And over here, this turns into cosine squared of x. Well, what's the identity for that? What's sine squared plus cosine squared?
I'm not sure.
It's 1.
Oh, 1.
So
okay.
now we have 1 over cosine x sine x, and that's the same as secant x. In other words, 1 over cosine x times 1 over sine x is the same as secant x times cosecant x. And now we've proven that the left side matches the right side.
Oh, okay.
Okay, let's go over all of our identities.
I think identities is the next thing that we're going to be getting into.
Well, you've had these identities, I think. Let's talk about there's only 11 basic identities that you need to do all of this proving trig identities. That's always done with the following 11 identities. Of these 11 identities, you only have to memorize 5 of them.
Okay.
I'll show you. You have 6 reciprocal identities. Okay? You have sine, you have cosine, and you have tangent. Well, You know the tangent. What's its reciprocal?
Sine over cosine.
No, that's its quotient identity.
Oh, okay, cotangent.
It's 1 over cotangent.
Oh, 1 over cotangent,
Okay.
sorry.
Now, the only thing left to figure out is, does the secant go with the sine or the cosine?
Secant goes with cosine.
Right. The first letters have to be different. C and S up here, cosecant, also C and S. But if you were to try putting the secant with the sine, you'd have S and S. Okay?
Mm-hmm.
So you have to memorize these three. And then, of course, that leads to cosecant is always 1 over sine. In other words, these two are, one means the other. And secant is 1 over cosine. And cotangent's 1 over tangent. So
Okay.
those are the 6 reciprocal identities. And you've been taught those already. You should know those.
Yeah.
Now let's talk about the 2 quotient identities. And that's the tangent equals sine over cosine. I'm leaving out the x just in the interest of not writing so much.
Mm-hmm.
You can't have a tangent just by itself. It has to have an angle. Okay?
Yeah.
So I'm implying that that's tangent of x, that's sine of x, that's cosine of x. And the other quotient identity is cotangent, which you don't have to memorize if you know tangent. So that's cosine over sine. So far we've had to memorize 3 things up top and only one of the quotient identities. And we already know 8 of the 11 identities. There are 3 more. There's 3 Pythagorean identities. And these all deal with squares. Sine squared x plus cosine squared x equals 1, always, no matter what x is. In other words, no matter what angle you take, if you take the sine of it and square it and add it to the cosine squared, you'll come up with 1.
Okay.
That's the first one they teach you. That's the easiest one to learn, to memorize. So you got to memorize that. And then there's really only one more that you have to memorize. And that's tangent squared of x plus 1 equals secant squared. That's a little different, notice.
Mm-hmm.
And finally, the third one is the cofunctions of the second one. Now, cofunction's not the same as reciprocal. The cofunction is the trig function with the word co in front of it.
Okay.
Cofunction of sine is cosine. Likewise, the cofunction of cosine is sine. You with me?
Yeah.
Cofunction of tangent's what?
Cofunction of tangents.
Put a co in front of it.
Cotangent.
That's what cofunction is. Just
Okay.
putting a co in front of it. Unless it already has a co in front of it, and then take it away. What's the cofunction of secant?
Cosecant.
There's your third and 11th identity. So, didn't have to really memorize the third one. You can figure this one out from the second one.
Okay.
So we have to memorize 2 Pythagorean identities, 1 quotient identity, and 3 reciprocal identities. That's a total of 6 out of 11. That's all you have to memorize. You can always work out the other 5.
Okay.
Okay? Now, knowing those identities is what verifying trig, if you walked in and could prove that you knew those identities backwards, forwards, and upside down, your teacher wouldn't bother sending you through verifying trig identities, because it serves one purpose and one purpose only, and that is to get you to memorize your trig identities.
Okay.
Let's try some. My book, there's all right. So this one. I'm going to leave out the x, like I said, just because there's an awful lot of writing here, but
Okay.
always presumed. Prove that that's equal to sine x. And the first rule is always work with the more complicated side and try to turn it into the other.
Okay.
So what's the first step you can do?
Well, I can change the top to 1.
Okay. And now we got 1 over cosecant x.
Cosecant x. And I can change that to secant of x.
Huh? What's the reciprocal of cosecant?
Secant. No, sine.
Sine. So that turns into sine. Don't get...
Oh, okay.
Remember, cofunctions are not reciprocals. They're a totally different category.
Okay.
So that turns into sine x. Problem proved.
Okay.
Okay? As long as we're talking about cofunctions, let's talk about them. Then we'll get back to doing your 11 major identities. Cofunctions have a purpose. The sine of x is always equal to its cofunction of 90 degrees minus x, and vice versa. In other words, cosine of x is equal to sine of 90 degrees minus x. Notice the cosine of 30 degrees is 1/2. Excuse me. The sine of 30 degrees is 1/2. That would make the cosine of 60 degrees 1/2. And that's true. Okay. And tangent of x equals its cofunction of 90 degrees minus x, and vice versa on that. And secant of x equals cosecant of 90 degrees minus x. They haven't taught you these yet. The only reason I did was because it's helpful in memorizing those first 11 identities. Because if you know what the cofunction is, it helps you with that third Pythagorean identity.
Okay.
Okay. Now, there's another technique when you're doing trig identities. Let me find one that uses that technique. Yeah, it's this. Believe it or not, those two are identities.
Okay.
Now, usually the more complicated, these are equally complicated. Actually, the left is a little more complicated.
Okay.
Because it's got the binomial term in the denominator. In other words, right, I can always split that up into 2 fractions, right? But the left, I can't do that. Well, whenever you see an expression like this, hard to do much with that. Unless you multiply top and bottom by the conjugate. Okay? So I'm going to, on the left side of the equation, multiply by 1 minus sine x. That's the conjugate of 1 plus sine x.
Yeah.
I got to multiply the top by 1 minus sine x, because I can only multiply stuff by 1. I can only multiply fractions by 1.
Uh-huh.
I'm going to leave the top alone, but the bottom, well, that's difference of perfect squares factored. So putting it back together again gives you that. And never multiply the top. Always leave it in factored form.
Okay.
The bottom is what you want to multiply. The reason is,
Okay.
now the bottom, what trig identity is that? If sine squared plus cosine squared equals 1, then what does 1 minus sine squared equal?
Just 1?
Huh?
Just 1?
No, here's the identity. Sine squared plus cosine squared equals 1. Now, you're rarely going to see that in these problems. What you're always going to see is an algebraic manipulation of that. In other words, what's 1 minus sine squared equal to?
1 minus sine squared.
Take over here and manipulate it so you can get 1 minus sine squared on one side.
1 minus sine squared. Equal to cosine squared?
Yeah. So I can replace that with cosine squared. Now I can cancel that cosine of x with one of these. And notice what I have. I have 1 minus sine x over cosine x.
Oh, okay.
That's what we were trying to prove.
Yeah.
Okay.
Okay.
So this is a little bit more complicated method where you have to multiply by the conjugate. The secret is always seeing this 1 plus sine x. It's really hard to do much of anything with that just using the regular identities. But if I can make that be 1 minus sine squared x, now I can replace it with cosine. In other words, I can replace those two terms with one term, cosine squared x, if I multiply by its conjugate.
Okay.
Okay. So let's do a few more of these tougher ones. Okay, here's one that looks tough. People find these really tough, but it's all about knowing your identities and knowing when to use the identity, which identity. In other words, like you said, tangent was sine over cosine, but it was also 1 over cotangent. Well, how do you determine which one to do? I'll show you right now.
Okay.
When you're dealing with squares, you probably want to deal with the Pythagorean identities.
Okay.
Well, what's the Pythagorean identity for that?
Cotangent squared of x. 1 over tangent squared of x?
That's an identity, but let's use the trig identity.
Oh, cosecant.
Well, we have the trig identity is cotangent squared plus 1 equals cosecant squared. Therefore, what is cotangent squared equal to?
Cosecant of x?
Cosecant squared of x minus 1. In other words, you always have to solve that algebraically. Okay? We're trying to replace cotangent squared of x. Well, that means we have to solve for cotangent squared. And I do that by subtracting 1 from both sides.
Okay.
So that turns into that. And then I am subtracting Cosine squared turns into 1 minus sine squared of x.
Okay.
And the other thing about proving identities is it's real easy to take the wrong tactic. And you end up off in the middle of the trees, unable to figure out how to make this thing look like this thing. Now, I can remove the parentheses, but then I'm going to have that minus 2 plus that, which doesn't help. So I'm going to go back and do it the way you suggested and see if that might be a better path. And trust me, this is very typical. It's you on these harder ones, it's real. Some of these harder ones, you can spend like 20 minutes and then finally give up and go back and say, I'm going to take a new path. It's a little bit like doing a maze. Okay. So let's do what you suggested. 1 over tan squared minus 1, let's use that reciprocal. Well, that's cosecant. Excuse me, that is secant squared. Now, whenever you have two fractions being added or subtracted, usually a good idea to go ahead and do the algebra. What's the common denominator?
Tan squared times secant squared of x.
Just write it like that. What goes up here and what goes right there?
1 minus 1.
No? Remember, when you find a common denominator, you have to make, let me redo this here. When you're doing fractions, if I said what's 1/3 minus 1/4, well, the common denominator is 12, but what goes in the upper left is 4. In other words, let me rewrite this a little bit better. Here's my common denominator. This is the best way to do it, actually. Now, I can easily figure out what goes here because it has to equal 1 over tan squared. Well, that's secant squared, right? Now I haven't changed it. You never want to change it. You just want to put something that's the equivalent there. And over here, this has to be tan squared.
Okay.
And now that whole thing, because they have common denominators, I can erase it. I can erase this denominator and extend my fraction line over and make that minus, and the fraction line goes to there. Okay, so that's what I've got.
Okay.
Now,
I see that.
Secant squared minus tangent squared, what's that equal to? Here's the Pythagorean identity that you memorized.
Secant squared is that just equal to 1?
Well, yeah. In other words, if I move the tangent squared on the other side, I got secant squared minus tangent squared equals 1. I can replace that with a 1. Now, I'm getting closer to my answer. I've got 1 over tangent squared secant squared. Well, now I can use the reciprocal identities to turn this thing on the lower left into cosine squared, which is the reciprocal of secant squared, times tangent squared, that's the reciprocal of tangent squared. So I've taken and moved and proven that that's what it is. That's the whole game, and it really is a game. It's like a crossword puzzle or a game of Sudoku or whatever. You just have to keep manipulating the left side until you're able to turn it into the right side. What happens is when you do about 50 of these, that's what they'll have you do, is about 50 of these. By the end of doing those 50, you're going to know your trig identities backwards and forwards.
Wow.
Okay? And notice that, like I said, we rarely see it tan squared plus 1 equals secant squared. What we frequently see is like secant squared minus tangent squared. The key thing is to remember that your Pythagorean identity, tangent's related to secant. So when you see something like secant squared and tangent squared, see if you can turn that into a number possibly. And like this case, we were able to turn that into the number 1.
Okay.
Okay. All right. Let's do another one because I think you get a little bit of a head start on these and you're going to be in much better shape. Some of these identities seem hard to believe, like this one. Tangent minus sine, tangent squared minus sine squared is the same as tangent squared times sine squared.
Okay.
Trig is it's full of all kinds of surprises. Okay, so let's do this one the same way that we did the last one. And the only reason that I know that it's better to use the quotient identities than the Pythagorean at the start is that the Pythagorean kind of leads you down a dead end, requiring a lot more work. In other words, all of these verifying trig identities, you can do some of them in 3 steps or 8 steps.
Oh, wow.
Counts just as well if you do it in 8 steps. Your teacher won't mark off. But obviously, you'd rather do it in 3 steps, right? All right. So start with the quotient identities on the left.
Tan squared is equal to sine squared over cosine squared?
Sine squared is equal to what?
Sine squared is equal to oh man.
Yeah. If you start
1 over
let's try to use this one. Oh, excuse me, my error. If tan is equal to sine over cosine, what is sine equal to?
1 over cosine, or 1 over
do the algebra.
Cosecant?
It's always a question of doing the algebra. No, just solve for sine.
Oh, tan times cosine.
Yeah. Tan, in this case, tan squared times cosine squared, because we started with sine. Okay. Let me erase it over here. And now, again, we need to subtract these. So, no, there's something else that I can do. Hold on a second. Yeah, let's find a common denominator, which is going to be cosine squared, and that's going to make that cosine to the 4th. You see that?
Yeah.
Okay. Doesn't help any, does it? Well, let's go back here. If you run into one that you can't make work, always resort to the last effort, which is to turn everything into sines and cosines, which is not a bad idea here because we already have a couple of sines. So if we just turn the tangent into sine over cosine, that might be the best thing to do.
Okay.
Subtract sine squared, which means if I want a common denominator, that's got to be sine to the fourth, right?
Mm-hmm. Yeah.
Excuse me, no. It's not sine to the fourth. It's sine squared cosine squared. The reason this is the best way to write it is because you can instantly tell if you've changed it going from there to there. In other words, if you look at the lower circle, I can cross out the cosines and I end up with sine. So I have not changed it. And that's what you want, is you don't want to change it. Okay. Now we have a common denominator. I can erase that. I can make the line go all the way, and I can subtract that. Now factor a sine squared out of the top. What do you get?
A factor sine squared out of the top. I get sine sine minus sine times cosine squared.
If I'm factoring sine squared out of that numerator, I'm dividing both terms by sine squared. That's what factoring is.
Mm-hmm.
Okay, so that's going to be 1 minus cosine squared.
Oh, okay.
So that's what the numerator happens to the numerator. This happens to the denominator.
Okay.
And 1 minus cosine squared is what?
Tan squared.
No, that's sine squared. Remember sine?
Oh, sine squared.
Pythagorean theorems, your sines and cosines go together, tangents go with secants, cotangents go with cosecants.
Okay.
Okay, now I can take that sine squared over cosine squared and turn it into what?
Oh, tan squared. Okay.
And that's how I get the right side. I end up with tan squared sine squared.
Man, I'm having a lot of trouble with these.
Well, these are hard. You're going to have trouble with them. But trust me, they'll get easier as you do them.
Okay.
The entire key is memorizing those 11 identities. Give me the 2 quotient identities.
2 quotient identities. Are those the sine and the cosine one, or tangent and cotangent?
Yeah.
Tangent equals 1 over cotangent.
That's the reciprocal identity.
Oh, then tangent equals cosecant minus 1.
Sine over cosine.
Sine over cosine.
So cotangent's equal to what?
Cosine over sine.
Yeah. And if you had one of those problems and there were a lot of sines and cosines and an odd tangent in there, well, you'd use this to turn, because you can turn the tangent into sines and cosines. Use quotient identities. You can't turn the tangent into sines and cosines using the reciprocal identities. Tangent turns into 1 over cotangent. So if you're trying to get stuff turned into sines and cosines, these quotient identities are important. And there's 3 Pythagorean. I think you probably have all of the reciprocal ones memorized. 3 Pythagorean. I'll start you off. What's the one involving sines and cosines? And they're all squared. Everything is squared with your Pythagorean identities.
Sine squared equals...
Well, sine squared plus cosine squared equals something.
Oh, sine squared plus cosine squared equals 1.
Okay, and then what's the one involving tangent?
Tangent squared plus, is it plus 1?
Uh-huh.
Equals cosecant
Secant.
squared.
Secant.
Oh, secant squared.
Remember that tangent goes with secant when you're talking Pythagorean identities.
Okay.
The third one is just the cofunction of the second one. Well, what's the
Yes, that's
cofunction of tangent?
cotangent squared plus 1 equals cosecant squared.
You got it. Okay, so that's not really that hard to memorize these 11.
Yeah.
It's somewhat difficult to figure out which one to use in a particular verifying trig identity problem. But let's do a few more. Let me find. Yeah, here's a good one. Tan to the fourth plus tan squared is equal to secant to the fourth minus secant squared.
Okay. Oh man, which side's harder? This is kind of the hard part to decide.
Think of three things. First of all, we're seeing exponents, so we're probably going to have to deal with the Pythagorean identities, right? I don't have any sines and cosines anywhere on the left or the right side, so I'm inclined not to turn this into sines and cosines. I'm going to try to use the Pythagorean identities involving tangents and secants.
Okay.
Now, before you use that, the other thing you want to consider is factoring. Almost always, when you can factor, factor.
Okay.
So factor something out of that left side.
You can factor out a tan squared.
Leaving?
It leaves tan squared plus 1.
Ah, that's an identity.
And tan squared plus 1 can turn into secant squared.
Okay, so we're there.
And
now,
then
there's no hard and fast rule that says you can't play with both sides.
okay.
So I could do something similar with the right side. The question is, do I have to? Right now I got tangent squared and secant squared. Let's see what happens if I factor a secant squared out. A lot of times by playing with both sides, it'll illuminate how we could play with just the left side and turn it into this.
Okay. Plus 1.
Minus
one. Sorry.
Now, what does that equal to?
Tan squared.
Yeah.
Oh, okay.
Oh.
Isn't that?
They're equal. So all I had to do is play with the right to see. Now I can go back and realize that hold on a second. If I turn this tan squared into secant squared minus 1, which it's equal to, now I have this, and multiply those two together and you get secant to the fourth minus secant squared. In other words, I didn't have to fool with the right side. Fooling with the right side did was tell me how I could completely turn the left side to look exactly like the right side, which is a little cleaner. It's a little bit cleaner way to do it. I don't know that you would lose points on a test if you fooled with the right side. I don't think so. There's no hard and fast rule that says you can't fool with both sides, but they generally don't want you to. they generally want you to take one side or the other and completely turn it into the other side. It's just that when I got to this step, I couldn't see how to do it. I was looking at tangent squared times secant squared. How in the world is that going to turn into secant to the fourth minus secant squared? Well, by doing this over here, I saw exactly how it does. Turns into that. And now I can see that tangent squared times secant squared is this times that. And then that multiplies out to give you the right side of the equation.
Okay.
These are actually fun once you do them. Well, for one thing is as you do them, you're going to get your identities down better and better and better. Every single one you do, you learn your identities. You solidify them in your memory. And that's what's important, is to make sure you know those 11 identities immediately.
Okay.
Okay? And that's the whole purpose. Now, sometimes you have to use those to solve a trig equation. Let's talk about that for a minute. If I had sine squared of x plus cosine of x minus, one second, I got to think about this for a second, minus 3 equals 0. Here is a real-life trig equation that you might run into with some sort of a problem. In other words, if you're looking at a real-world problem and it gives you this equation out and you have to solve it, solving trig equations is tough if you have different trig functions. Very, very difficult to solve if I end up with a sine and a cosine in it. So I'm going to solve it by turning that into 1 minus cosine squared plus cosine x. Let's make that a plus 3. Plus 3 equals 0. Now, if I turn this into a quadratic, this is what I call a quadratic in disguise. I wanted to leave that at plus 1. Figuring them out backwards is harder than solving them. All right. Now, if I simplify this, I get minus cosine squared of x plus cosine of x plus 2 equals 0. Divide everything by minus 1, and I get cosine squared of x minus cosine of x minus 2 equals 0. And notice how you can solve that. Do you have a clue as to how you would solve that?
You could factor it?
Yeah, that is a quadratic. It's what I call a quadratic in disguise. In other words, it's not a quadratic in x, it's a quadratic in cosine x.
Cosine.
Cosine x. And if I'm going to factor it, it's going to be split the cosines up. I'm going to determine my signs. They have to be opposite. Factors of 2 that subtract to 1. And the 2, the bigger factor.
2 and 1.
Sign in the middle, and there you go. Now I've solved the equation. Either cosine x equals minus 1 or cosine of x equals 2.
Okay.
Okay. Now, the second one's impossible.
Because you can't have a negative.
Yeah, well, it can't be a number greater than 1 or less than minus 1.
Yeah.
So that's extraneous. You frequently end up with extraneous solutions. So now the only solution, our goal is to solve for x, not cosine x. But if cosine x equals -1, what's x equal?
Cosine x equals -1. X equals... Wait a second.
Here, I'll label everything.
2 pi. Oh, x equals pi.
Yeah. And that's the answer. X equal pi. Assuming that they said the domain for x is the unit circle, which they usually do on these equations.
Mm-hmm.
Okay. So here was an equation where we had to use an identity to solve it. We had to use the Pythagorean identity. So it's not like these identities are worthless. They're very worthwhile. It's just that when you're verifying trig identities, there aren't any real-world problems that require you to verify trig identities.
Yeah.
Worst thing a teacher can do is give you multiple choice on verifying trig identities. That is about 5 times harder than verifying a trig identity, believe it or not. It's the only thing, it's the only math problem I can think of where giving you multiple choice makes it a lot harder. And the reason is that they're about to give you 50 or 60 practice problems on verifying identities, and every one of them is an identity. So you learn really well how to verify trig identities. What you don't learn is to identify when it's not an identity. And that's what you have to do on multiple choice. In other words, when they give you an identity and they give you 4 possible choices, you have to essentially eliminate 3 of them because you don't know which one the identity is. So you go to work on each one trying to prove it, and that's going to take all day. Or you can try to disprove it, and you don't know how to do that. They haven't taught that to you. They haven't taught it to me. I don't know how to disprove an identity. All of the problems are proving identities that are identities. So hopefully your teacher isn't cruel and unusual and won't give you multiple choice on proving trig identities when you get to that.
My old teacher might have been. I don't think this one is.
I've seen some teachers do it, not many. I would say about 1 every 5 trig students I get gets a teacher that wants to have a multiple choice trig identity on there. And those are brutally tough. Let's think. Last things about trig. Since we've used all but 6 minutes on trig, why don't we stick with trig for the rest of this session? That's a good one. Might take 6 minutes to do this one.
Okay.
Although probably not, but keep in mind what I said, that sometimes you can go on the wrong path and not recover from it. You really do get lost in the woods because you can't see the trees because you're in the woods.
Okay.
That is an identity.
Oh, wow.
So we have to prove it. So what do you need to do?
You have secant on the other side. I think we need to change the cosines to secant because...
Not yet. We're looking at a very complicated expression on the left here. Think of adding these 2 fractions together. What's going to be your common denominator?
If you add them, wouldn't it just be 1 or 2?
No, remember, let's review a little algebra. 1/3 plus 1/4. What's the common denominator?
12.
You get that by multiplying 3 times 4.
Oh, okay.
12 goes there. 12 goes there, and then I have to figure out what this numerator is. Well, it's got to be 4. My whole goal is to not change the fraction 1/3. This one's got to be 3, so I get 7/12.
Okay.
Okay? When I say add fractions, that's what I mean. And
Okay.
the advantage of doing that here is that the common denominator is going to be 1 plus sine times 1 minus sine. Well, that's difference of squares factored, so when I multiply it back together again, it's 1 minus sine squared.
Oh, and that, okay.
And that I'm going to be able to turn into cosine squared.
Mm-hmm.
Okay? So first let me write the common denominator. And I really love doing it like this because you can instantly check your answer to make sure you have not changed the fraction. What goes up here on the left?
On the left, it would be 1 minus sine square, or 1 minus sine of x times cosine of x.
Yeah, and don't distribute that. Just leave it just like that.
Okay.
Over here on the
And then on 1 minus sine x, or 1 plus sine x, sorry, times cosine x.
Okay, we know this is going to turn into 1 minus sine squared, which turns into cosine squared. This is going to turn into 1 minus sine squared, which turns into cosine squared. So now I have 1
and the one
I'm thinking here. What is our answer? Our answer is 2 secant?
2 secant x, I think.
2 secant x. Okay. Well, you can kind of see where the 2 secant x. Well, if I multiply these and add them, I'm going to see a 2 there. Let's factor out a cosine x from the numerator. Just because I can. Cosine x, what left over is 1 minus sine x plus 1 plus sine x. Right? That's my new numerator. Still over cosine squared x. Now notice that cancels with the squared. This sine x cancels with that sine x, and I'm left with 2. 2 over cosine x. What's 2 over cosine x equal to?
2 secant x.
Yeah.
Okay.
And that's how.
Man. That's crazy.
It is a little crazy. You get used to thinking in certain ways, and one of the things is whenever you have a 1 minus sign and you're adding it to a 1 plus sign, think common denominator, because that whole thing's going to turn into cosine squared. Or if you have a 1 minus sign or a 1 plus sign and you're not adding it, think multiply by the conjugate, because then you can turn it into a single cosine squared.
Okay.
All right?
Okay.
Cool. I have a 7 o'clock.
Yeah, no worries. Sounds good.
Okay. Talk to you on Wednesday. Wednesday at 3 or 3:15?
3. I think it's 3:15.
Well, I wasn't sure. You signed online, and I know last week you needed to do it at 3:15. I was wondering if the same thing was true.
Yeah, 3:15.
Okay.